In the previous session we were talking a bit about the symmetric group. Remember, that's the group of all permutations of a given number of objects, say little n. Here, let's choose n to be small, so very small, 3. So we're just permuting 3 different objects. And you know the number of permutations of 3 objects is 3 factorial, and so that's just 6, right? And here are the elements of that group, the symmetric group, 3 objects. Here's your unit, right? And, well, I mean, you can label them any way you like, but what's going on here? So R, can you see that? Can you see these 1, 2, 3s? They're shifting like one position to the left, so then you get 2, 3, 1, and you can do it twice. So this 3 moves up 2 positions, and the 1 wraps around, and again, the 2, 1, 2, okay? And the X, Y, Z, the 1 doesn't change, the 2 doesn't change, the 3 doesn't change, so systematic. So there are your 6 elements of this group, the symmetric group, n is 3. And if you have the elements, you can work out the group table, and here it is. It's a bit of work, even with so few objects as 3. Therefore, the size of the group, the group's order, is 6, and therefore the number of entries in the group table will be the order squared. So that's 6 squared, so 36 entries. So I wrote it out beforehand because it's tedious. And there's the group table. Now you look at it, and except for translation, translating between the symbols of one group and the symbols of the elements of one group and the symbols of the element of another group, except for translation, you probably seen this kind of thing before. It looks familiar, right? And the answer is yes, it does. So this is the group table for S3, right? The symmetric group, the group of all permutations of 3 objects, or permuters, if you want to call it that way. Now, this the reason why it looks familiar is because this group happens to be isomorphic to the group of rotations, symmetry operations of the equilateral triangle. Remember that? You have to go back a few lectures. But I've drawn the equilateral triangle here. Equilateral just means equal sides. The lengths of each side of your triangle is the same. And next lecture, 13, that notion comes back. It's the theme of the whole lecture on circle. I think it's, let's see how to pronounce it. Di meaning 2, dihedral, like 2 sides, dihedral groups. So this equilateral triangle is the simplest example of a dihedral, a dihedron. So equilateral polyhedron, every side on the polyhedron, like a decagon with 10 sides, or a pentagon with 5 sides, or a hexagon with 6 sides, and so on. Each side is equal length. And that's a dihedron, the generic term. Okay, so you've seen the group table for an equilateral triangle. That group is labelled D3, and you have a look at this. You'll see it again next lecture set. So we've been introduced to the first one, but there's there's an infinite number of them. Okay, so how about how to prove these 2 groups are in fact isomorphic? Well, one is just by inspection. You just look at the 2 group tables, and you find that you can translate back and forth, because if these 2 groups are isomorphic, you can do that. So you just translate the unit in this group maps to the unit in the triangle. Don't rotate anything, and so on. Okay, so I've put the arrows both ways, isomorphic. And that's just by visual inspection. You just look at the two group tables and you can see this obvious translation. Now remember, go back to the previous lecture, doing that kind of thing in general is hazardous. You can remember that awful example where to prove that two groups were isomorphic, we were swapping columns and swapping rows multiple times and then translating, and oh, it was a mess. So we agreed there had to be a better way, and the better way, which we then did many times in last lecture, which was a very long lecture, with turned out to be 30 clips, 30 components of around 11, 12, 13 minutes each, so very long lecture. So we did the general method, the more powerful method, to show two groups are isomorphic, and you probably remember. So just by visual inspection method, like this, it'll work sometimes. I mean, if the translation is easy, but in general it's risky, right? So better to use the general method of proving bijection, and well formed, of course. Bijection and the f of mn thing. I don't have a label for it. I just all right. So let's here the f. We have to prove that the function mapped to mn is equal to f of m times f of n. Right? And you need that to prove that the corresponding elements of the two group tables map to each other. All right. So, how using this more general, more powerful method, how could we show these two groups isomorphic? So, in a sense, what we're doing now is throwback a bit to the previous lecture, lecture 11. But it's useful. We can show a type of group that we'll be dealing with next lecture, in lecture 13, is actually isomorphic to the symmetry group. So that's useful to know, and we can use that kind of information as we build further in the future. Okay? All right. So how to show these two isomorphic? Well, we need a function, right? We're going to map between the two, and first creative choice is which direction are we going to go. We're going to map this to this, we're going to map this to this, so 50-50 chance if you're not thinking. So you need to choose, it's a creative choice, you need to choose an f, not just the directions, that's part of it, but also what's an intelligent choice, what's the meaning of the symbols that you use. Okay, so let's choose to map from the operations of the symmetry operations of the triangle, okay, and map that into the symmetric group. Okay, so we're going to try to map from D to S. Okay, so that means we need a general element of D here. And this D, what is it? It's the symmetry operations of a triangle. So what's it doing? So just take some generic, some arbitrary member of this group. Right? Let it be phi. This is symbol here, phi, like a circle with a vertical stroke through it. So phi, Greek letter. Okay, so let that be an arbitrary member of this group, this symmetry group, symmetry operations of the equilateral triangle. Okay, now what's that actually doing? Well, we've got there are six symmetry operations on the equilateral triangle, and effectively, when you apply one of these operations here. All you're doing is just rearranging these three numbers. Okay, so this function phi is mapping this 1 into some phi of 1, right? And phi of 1 could be 1 or 2 or 3. Okay, and similarly, this function maps this 2, and like these what are these three things? They're the vertex, like the point of the triangle. And you'll have 3 points, three vertices is the plural. Okay. So this phi maps 2 into 5, 2, and maps 3 into 5, 3, whatever it is. So yeah, this could be 1, 2, or 3. This could be 1, 2, or 3, and this could be 1, 2, or 3. But no 3 of them are equal, right? It's got to be a one-to-one mapping. It's got to be a bijective mapping. Okay, but effectively that's what phi is doing. It's mapping these vertices, these numbers, if you like, into vertices. Right? So it maps 3 vertices into 3 vertices. Okay, and what you start with, the labeling is anti-clockwise. Right? So 1, 2, 3. And that set 1, 2, 3 gets mapped into phi 1, phi 2, phi 3. Right? So here's the suggestion. So here's your function, and you know, as I was saying in the previous lecture, choosing your function is pretty well half the task done, half your proof, because everything else, all the proof from then on, depends on this critical choice. Right? So the choice of a good function, of a good mapping, from which group to which group, or rather from which set to which set. Okay, so.